Good evening, one and all. I'm Vishaka from IETE-ISF, and I graciously welcome you all to today's session. Our enlightening session today is focused on deep learning and neural networks. Neural network is a computational learning system in machine learning algorithms that uses a network of neurons, or basically mathematical functions, to translate the input data to a desired output. They are used in a variety of applications such as pattern recognition, face recognition, self-driving cars, and many more. We have a well-renowned guest here with us tonight to take this session on deep learning and neural networks. None other than Dr. Joshua Starmer, the founder and CEO of StatQuest. Hello, sir.
Hello, hello. It's good to be here. Hold on, let me get my cat down. I've got a little silly song for you guys. Hip 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 hooray. We're gonna talk about neural networks today. Hip hip hooray. StatQuest. Bam.
Yay, that was amazing. Welcome, sir. So, Josh Starmer started StatQuest as an attempt to explain statistics to his former co-workers who were all genetic researchers at UNC Chapel Hill. They didn't always know what to do with the data generated, mostly because of the confusing terminology, which was typically communicated using equations. He made these stat quests to explain statistics, machine learning, and data science, stripping away the terminology, which made scary concepts so easy to understand and grasp. This eventually became his passion on YouTube, where he's making the lives of all the budding data scientists and statisticians super easy. Bam! And if that was enough, he also writes and records songs, instrumental music that has been commissioned by dance companies, licensed for use in TV commercial, and featured in movies as well. He also makes his StatQuest videos so entertaining and easy to understand by interweaving statistics and music, not to mention the amazing intro songs in the videos, and that is a double bam. And
Double bam.
yeah, double bam. IETE takes immense pleasure in welcoming Dr. Josh Stammer for his session on neural networks today. And also, just as we progress through the session, if you have any doubts or queries, kindly post them in the live chat for us to take it up. Over to you, sir.
Okay. Hooray. Hello, everybody. I'm Josh Starmer, and welcome to StatQuest. Today, we're going to talk about neural networks part one, inside the black dot box. This is actually just the first part of several things we're going to talk about. Um, we're going to, I could go a number of different directions today, but I think what we're going to do is we're going to start with a basic neural network, and we're going to show how that neural network is used for image classification. And we'll also, if we have time, and I hope we have time, I've got something very special that I haven't shown anybody at all in the whole wide world about how the convolutional neural network that we use for image classification, how that can be used for time series data like financial data. So we'll just see what we can cover, and we're just going to get as far as we can, and and hopefully we'll have time for some questions at the end. So without further ado, let's get inside of the black box. So neural networks, one of the most popular algorithms in machine learning, cover a broad range of concepts and techniques. However, people call them a black box because it can be hard to understand what they are doing. The goal of this series is to take a peek into the black box by breaking down each concept and technique into its components and walking through how they fit together step by step. In this first part, we will learn about what neural networks do and how they do it. Beep, boop, beep, boop, beep. And in the second part, which we won't talk about today, but is online, we'll talk about, I do talk about how neural networks are fit to data with a method called backpropagation. Beep, boop, beep, boop, beep, boop. And then, and this is what we'll talk about today, variations on the simple neural network presented in this part. And we're going to get all the way into deep learning. Yes. Yeah. Sure. Yeah. Hello. Well, are we live or should I start over?
Yes, sir. Sorry for the delay. I can start it. It's working now.
Great. That's great to hear. Should I start from the beginning or should I just start where I left off?
Would be better if we start from the beginning, sir. There's been an issue, so if you don't mind.
Hello, I'm Josh Starmer, and welcome to StackQuest, and welcome to this awesome hackathon. It's an honor to be able to speak today. Thank you very much for inviting me. Um, so without further ado, we're going to talk about neural networks today. We're going to do 3 parts from my series on neural networks. We're going to do part 1, 4, and I believe 11. We're jumping around, but I just want to show you some of the highlights of what neural networks can do and how they do that. So today we're going to look inside of the black box. So neural networks, one of the most popular algorithms in machine learning, cover a broad range of concepts and techniques. However, people call them a black box because it can be hard to understand what they're doing. The goal of this series is to take a peek into the black box by breaking down each concept and technique into its components and walking through how they fit together step by step. Beep, boop, beep. In this first part, we're going to learn about what neural networks do and how they do it. Beep, boop, beep, boop. In part 2, which we're not going to talk about today, but it's available online, I talk about how neural networks are fit to data with something called backpropagation. Boop, 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 boop. Then we'll talk about variations on the simple neural network presented in this part, including deep learning. Boop, 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 boop. Okay, I've got some crazy awesome news. I have a new way to think about neural networks that will help beginners and seasoned experts alike gain a deep insight into what neural networks do. So even if you're familiar with neural networks, you still stand to gain a lot of knowledge into the inner workings of neural networks. For example, most tutorials look cool, use these cool looking but hard to understand graphs. And they use fancy mathematical notation to represent neural networks. In contrast, I'm going to label every little thing on the neural network to make it easy to keep track of the details. And the math will be as simple as possible while still being true to the algorithm. And I want to make a point of this. People have actually asked me this online. What I'm about to show you is so simple that people have a hard time believing that it's true. They just assume that neural networks are more complicated than they're capable of understanding, and they just don't believe that this is the actual mathematics that is going on in neural networks. But the reality is that it is. I'm not dumbing it down. All I'm doing is clarifying it. This is the exact mathematics that are used for neural networks. So even though you are able to understand it, don't panic. This is actually what's going on. There's no need to fear that I'm dumbing it down. I'm actually bringing you up and just demystifying and removing all of the clutter that makes neural networks hard to understand. This is the real deal. Okay, and these differences will help you develop a deep understanding of what neural networks actually do. A lot of people understand neural networks on a high level, but they don't know what they're actually doing. And by the end of today, you will understand exactly what neural networks do. So, with that said, let's imagine we tested a drug that was designed to treat an illness. And we gave the drug to three different groups of people with three different dosages. We had a low dosage, a medium dosage, and a high dosage. The low dosages were not effective, so we set them to 0 on this graph. In contrast, the medium dosages were effective, so we set them to 1. And the high dosages were not effective, so we set those to 0. Now that we have this data, we would like to use it to predict whether or not a future dosage will be effective. However, we can't just fit a straight line to the data to make predictions, because no matter how we rotate the straight line, it can only accurately predict 2 of the 3 dosages. The good news is that a neural network can fit a squiggle to the data. The green squiggle is close to 0 for low dosages and close to 1 for medium dosages and close to 0 for high dosages. And even if we have a really complicated data set like this, a neural network can fit a squiggle to it. In this stat quest, we're going to use this super simple data set and show how this neural network creates this green squiggle. But first, let's just talk about what a neural network is. A neural network consists of nodes, these boxes in the figure, and connections between the nodes, which are these arrows with the numbers on them. Note, the numbers along each connection represent parameter values that were estimated when this neural network was fit to the data. For now, just know that these parameter estimates are analogous to the slope and intercept values that we solve for when we fit a straight line to data. So it's just like when we do least squares or linear regression, we're solving for the slope and intercept of the best fitting line. We do a similar thing for neural networks. We have a pile of data and we fit that neural network to the data using a method called backpropagation, which we'll talk about another day. But basically, that estimates these parameters, these numbers. So likewise, neural network starts out with unknown parameter values that are estimated when we fit the neural network to a data set using a method called backpropagation. And we'll talk about how backpropagation estimates these parameters in part 2 in this series, which is a video that's online. We're actually not going to talk about it today. But if you want to learn more, you can check it out on statquest.org. For now, however, just assume that we've already fit this neural network to this specific data set. And that means we have already estimated these parameters. Also, you may have noticed that some of the nodes have curved lines inside of them. These bent or curved lines are the building blocks for fitting a squiggle to data. The goal of this stat quest is to show you how these identical curves can be reshaped by the parameter values and then added together to get a green squiggle that fits the data. Note, there are many common bent or curved lines that we can choose for a neural network. This specific curved line is called soft plus, which sounds like a brand of token functions. When you build a neural network, you have to decide which activation function or functions you want to use. When most people teach neural networks, they use the sigmoid activation function. However, in practice, it is much more common to use the ReLU activation function or the soft plus activation function. So we use the soft plus activation function in this stat quest. Anyway, we'll talk more about how to choose activation functions later in this series. Note, this specific neural network is about as simple as they get. It only has one input node where we plug in the dosage, and only one output node to tell us the predicted effectiveness, and only two nodes between the input and output nodes. However, in practice, neural networks are usually much fancier and have more than one input node, more than one output node, different layers of nodes between the input and output nodes, and a spider web of connections between each layer of nodes. Oh no, it's another terminology alert. Layers of nodes between the input and output nodes are called hidden layers. When you build a neural network, one of the first things you do is decide how many hidden layers you want and how many nodes go into each hidden layer. Although there are rules of thumbs for making decisions about the hidden layers, you essentially make a guess and see how well the neural network performs, adding more layers and nodes if needed. Now, even though this neural network looks fancy, it is still made from the same parts used in this simple neural network, which only has one hidden layer with two nodes. So let's learn how this neural network creates new shapes from the curved or bent lines in the hidden layer and then adds them together to get a green squiggle that fits the data. Note, to keep the math simple, let's assume dosages go from 0 for low to 1 for high. Boop, boop. The first thing we're going to do is plug the lowest dosage, 0, into the neural network. Now, to get from the input node to the top node in the hidden layer, this connection multiplies the dosage by negative 34.4 and then adds 2.14. And the result is an x-axis coordinate for the activation function. For example, the lowest dosage, 0, is multiplied by negative 34.4, and then we add 2.14, get 2.14 as the x-axis coordinate for the activation function. To get the corresponding y-axis value, we plug 2.14 into the activation function, which, in this case, is the soft plus function. Note, if we had chosen the sigmoid curve for the activation function, then we would plug 2.14 into the equation for the sigmoid curve. And if we had chosen the ReLU bent line for the activation function, then we would plug 2.14 into the ReLU equation. But since we are using soft plus for the activation function, we plug 2.14 into the soft plus equation. Boop. And the log of 1 plus e raised to 2.14 is 2.25. Note, in statistics, machine learning, and most programming languages, the log function implies the natural log or the log base e. Why they don't just use the natural log, the ln symbol for natural log, I do not know. They just use the log function, and we're all supposed to know that that means log base e. So there. Anyways, the y-axis coordinate for the activation function is 2.25. So let's extend this y-axis up a little bit and put a blue dot at 2.25 for when dosage equals 0. Now we increase the dosage a little bit and plug 0.1 into the input. The x-axis coordinate for the activation function is negative 1.3, and the corresponding y-axis value is 0.24. So let's put a blue dot at 0.24 for when dosage equals 0.1. And if we continue to increase the dosage values all the way to 1, the maximum dosage, we get this blue curve. Note, before we move on, I want to point out that the full range of dosage values from 0 to 1 corresponds to this relatively narrow range of values from the activation function. In other words, when we plug dosage values from 0 to 1 into the neural network, then multiply them by negative 34.4 and add 2.14, then we only get x-axis coordinates that are within the red box. And thus, only the corresponding y-axis values in the red box are used to make this new blue curve. Bam. What I'm trying to say here, to summarize, we have this curve that actually goes from negative infinity to positive infinity. But due to the way the neural network was fit to the data originally, we're only using a small piece of it. And we're using a specific small piece of it. And then later on, we're going to use a different piece to create a different shape. And so this is a hint as to how activation functions are used. Okay, now we scale the y-axis values for the blue curve by negative 1.3. For example, when dosages equal 0, the current y-axis coordinate for the blue curve is 2.25. So we multiply 2.25 by negative 1.3 and get negative 2.93. And negative 2.93 corresponds to this position on the y-axis. Likewise, we multiply all of the other y-axis coordinates on the blue curve by negative 1.3. And we end up with a new blue curve. Bam. Now let's focus on the connection from the input node to the bottom node in the hidden layer. However, this time we multiply the dosage by negative 2.52 instead of negative 34.4, and we add 1.29 instead of 2.14 to get the x-axis coordinate for the activation function. Remember, these values come from fitting the neural network to the data with backpropagation, and I talk about that in part 2 in this series, which is available online at statquest.org. Now, if we plug in the lowest dosage, 0, into the neural network, then the x-axis coordinate for the activation function is 1.29. Now we plug 1.29 into the activation function to get the corresponding y-axis value and get 1.53. And that corresponds to this yellow dot. Now we just plug in dosage values from 0 to 1 to get the corresponding y-axis values. We get this orange curve. Note, just like before, I want to point out that the full range of dosage values from 0 to 1 corresponds to this narrow range of values from the activation function. In other words, when we plug dosage values from 0 to 1 into the neural network, we only get x-axis coordinates that are within the red box. And thus, only the corresponding y-axis values in the red box are used to make this new orange curve. So we see that fitting a neural network to data gives us different parameter estimates on the connections, and that results in each node in the hidden layer using different portions of the activation functions to create these new and exciting shapes. Now, just like before, we scale the y-axis coordinates on the orange curve, only this time we scale by a positive number, 2.28. Boop, 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 boop. And that gives us this new orange curve. Now the neural network tells us to add the y-axis coordinates from the blue curve to the orange curve. Beep, boop, boop, boop. And that gives us this green squiggle. Then, finally, we subtract 0.58 from the y-axis values on the green squiggle. We have a green squiggle that fits the data. Bam! Now, if someone comes along and says that they are using dosage equals 0.5, we can look at the corresponding y-axis coordinate on the green squiggle and see that the dosage will be effective. Or we can solve for the y-axis coordinate by plugging 0.5 into the neural network and do the math. Boop, boop, beep, boop, beep, boop, beep, boop, boop. Beep, boop, boop, boop. Beep, boop, 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 boop. Beep, boop, 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 beep, boop, boop. Bam. And we see that the y-axis coordinate on the green squiggle is 1.03. And since 1.03 is closer to 1 than 0, we will conclude that dosage equals 0.5 is effective. Bam! Now, if you've made it this far, you may be wondering why this is called a neural network instead of a big fancy squiggle fitting machine. The reason is that way back in the 1940s and 50s, when neural networks were invented, they thought the nodes were vaguely like neurons, and the connections between nodes were sort of like synapses. However, I think they should be called big fancy squiggle fitting machines because that's what they do. Note, whether or not you call it a squiggle fitting machine, the parameters that we multiply are called weights, and the parameters that we add are called biases. And note, this neural network starts with two identical activation functions, but the weights and biases on the connections slice them, flip them, and stretch them into new shapes, which are then added together to get a squiggle that is entirely new. And the squiggle is then shifted to fit the data. Now, if we can create this green squiggle with just two nodes in a single hidden layer, just imagine what types of green squiggles we could fit with more hidden layers and more nodes in each hidden layer. In theory, neural networks can fit a green squiggle to just about any data set, no matter how complicated. And I think that's pretty cool. Triple bam. All right, so we finished the first part. Now let's move on to this second part of this seminar. Oops. Let's do this again. What am I presenting? Let's do this correct. Okay, there we go. So we're skipping the parts on back propagation, which you're, by the way, more than welcome to watch. I've also got a video on the ReLU activation function, which we're going to use in this portion of the seminar. So you're going to get to see the ReLU activation function in action, but it's super simple and super straightforward. So I think you'll be able to follow it, no problem. Anyways, now we want to talk about a slightly more complicated neural network that has multiple inputs and outputs. So far, the neural networks that we've looked at have been super simple and only predict whether or not the dosage of a drug will be effective. The neural networks just have one input node, one output node, and when there's only one input node, then the data we are using to make predictions, in this case, dosages, can all fit on the x-axis of this graph. In other words, the input is one-dimensional since it only needs one axis in the graph. Likewise, a single dimension, the y-axis, represents the output values. Combined, we get a two-dimensional graph with input dosage on the x-axis and the output drug effectiveness on the y-axis. Because the input and the output combine to form a two-dimensional graph, we can see how the weights and biases in this neural network slice, flip, and stretch the curved or bent activation functions into new shapes. So in the last part, we were looking at the soft plus function. Now we're looking at the ReLU activation function. So the shapes that we're using are slightly different than before, but it's the same basic idea. We do the math, we find the x-axis coordinate, we plug that x-axis coordinate into the activation function to get the corresponding y-axis coordinate, and then we can plot that on the graph. And then we sum the two it's not the two activation functions, but the two parts of the activation functions. We sum those together, and then we shift that sum. And then in this case, we're running everything through a final activation function. Again, this is the ReLU activation function. That gives us our final output. So we can see, to compare and contrast with the soft plus activation function that we were using before, with the ReLU activation function, we get a much more sort of precise fit to the data. And ReLU is also slightly easier to do mathematically. And so that's one of the reasons why ReLU is very popular for deep learning. Bam. Now let's look at a more complicated neural network that has more than one input node and more than one output node. Now, this neural network may look really fancy, but all it does is take two measurements from an iris flower, the width of a petal, which is this part of the flower, and the width of a sepal, which is this part of the flower. And with that information, it predicts the species, either setosa, versicolor, or virginica. Now, raise your hand if you already knew that this was a sepal and not a petal. Not me. I thought they were all petals. Anyway, to keep things simple at the start, let's begin with both input nodes, with just one output node for setosa. Later on, we'll add the other two input nodes, or excuse me, the other two output nodes. For now, let's just keep things simple and just use one output node. Now let's see what happens when we plug values for petal width and sepal width into this simplified neural network. Since we have two inputs and one output, if we are going to draw a graph of what's going on, then we need a three-dimensional graph. The inputs, petal width and sepal width, each get an axis. And the output, the prediction for setosa, gets the y-axis. Note, to keep the math simple, I scaled the inputs to be between 0 for the smallest value and 1 for the largest value. So let's start in this corner where petal and sepal width equals 0 and plug those values into the neural network. First, let's determine the x-axis coordinate for the top node in the hidden layer. We multiply the petal width by the weight associated with its connection to the top node in the hidden layer, -2.5. And we multiply the sepal width by the weight associated with its connection to the top node in the hidden layer, 0.6. Then we add the two terms together and add the bias, 1.6. And that gives us the x-axis coordinate for the activation function, which is 1.6. Now we plug 1.6 into the ReLU activation function to get the y-axis coordinate 1.6. So the ReLU activation function is simply the max of 0 or the number you plug into it. And what that means is if you plug a negative number into the RailU activation function, the output is always 0. And if you plug in a positive number, a number that's greater than 0, then the output is the same as the input. So that's all there is to know about the RailU activation function. Anyways, that's our y-axis coordinate. And it's the reason why it's a y-axis coordinate is because 1.6 is greater than 0. And 1.6 corresponds to this blue point on the graph where petal and sepal widths are both 0. Now let's increase petal width to 0.2, but keep sepal width at 0. Now, when we do the math, we get 1.1 for the x-axis coordinate and 1.1 for the y-axis coordinate. Again, that's just because 1.1 is greater than 0. And 1.1 corresponds to this blue point on the graph. Likewise, when we increase petal width to the maximum value, 1, but keep sepal width at 0, we get these blue dots. Now let's increase sepal width to 0.2 and run values for petal width from 0 to 1 through the neural network. Likewise, if we keep increasing sepal width to 1 for different values of petal width, we get this blue bent surface. The bend corresponds to the points where the RailU activation function set the y-axis values to 0. So anytime the input to the RailU was negative, the output was 0, and that's where what that bend corresponds to. Now we multiply the y-axis value for each point by negative 0.1. For example, the original y-axis value for this point, when petal and sepal widths are both 0, is 1.6. And 1.6 times negative 0.1 equals negative 0.16. So the final point is here. Likewise, when we multiply all of the other y-axis coordinates by negative 0.1, we get this final blue bent surface. Now we do the exact same thing for the connections to the bottom node in the hidden layer. Beep, boop, beep, boop, beep, boop. And we end up with this orange bent surface where the bend occurs where the RailU activation function set the y-axis values to 0. Then we multiply each y-axis coordinate by 1.5 to get the final orange bent surface. Now we add the y-axis coordinates on the blue bent surface to the y-axis coordinates on the orange bent surface. For example, the y-axis coordinate for this blue point is negative 0.16. And we add the y-axis coordinate for this orange point, 1.05, to get 0.89, the y-axis coordinate for this green point. Anyways, we do that for every single point, and ultimately, we end up with this green crinkled surface. Now the last thing we do is add the final bias, 0, to each y-axis coordinate. And since adding 0 doesn't change the green crinkled surface, this is the output for setosa. Bam! Looking at the green crinkled surface, we see that the value for setosa is highest when the petal width is close to 0. And the value for setosa is lowest when the petal width is close to 1. Note, remember that we scaled the inputs to be between 0 and 1. Thus, petal width equals 0 does not imply that the petal is 0 centimeters wide. Instead, 0 refers to the smallest width in the training dataset. Likewise, 1 means the largest width in the training dataset. Small bam. Now, to review the concept so far, when we have two inputs, the neural network creates curved or bent surfaces. that are added together to make a new crinkled surface that, in this case, we can use to make predictions about whether or not the species of an iris is setosa. For example, if we found this iris while walking in the woods and the scaled petal width was zero point 0.5 and the scaled sepal width was 0.37, then we could look at at the y-axis value on the green crinkled surface that corresponds to these measurements and see that this particular iris is probably not setosa because the y-axis value is closer to 0 than 1. And this is confirmed when we run the numbers through the neural network and get 0.09. Bam. Now that we have a green crinkled surface for setosa, let's determine the output for the second species, versicolor. Just like before, we'll start with the connections to the top node in the hidden layer. And because the weights and biases are the same as before, we start out with the same blue bent surface. However, because we will multiply the y-axis coordinates by 2.4, let's change the range of the y-axis from 0 to 2 to -6 to 6. Bam. Now, multiplying the y-axis coordinates by 2.4 gives us this final blue bent surface. Now we create the orange bent surface from the bottom node in the hidden layer and multiply the y-axis coordinates on the orange bent surface by -5.2. Now we add the y-axis coordinates from the two bent surfaces together to create this red crinkled surface. Lastly, we add the final bias 0 to the y-axis coordinates on the red crinkled surface, and that gives us the final surface for predicting if the iris species is versicolor. Now, I'll admit, it's hard to see what values for petal and sepal widths will give versicolor a high score on this red crinkled surface. But when we change the y-axis scale from -6 to 6 to -0.5 to 1, we see that when petal width is close to 0.4, we will get a high value for versicolor. Double bam! Now, just like we did for setosa and versicolor, let's determine the crinkled surface for Virginica. Just like before, we start with the blue bent surface from the top node in the hidden layer. But now we multiply the y-axis coordinates by -2.2. Just like before, we create the orange bent surface from the bottom node in the hidden layer. But now we multiply the y-axis coordinates by 3.7. Now we add the y-axis coordinates for the two bent surfaces together to get this purple crinkled surface. Lastly, we add the final bias 1 to the y-axis coordinates on the purple crinkled surface. And that gives us the final surface for predicting if the iris species is Virginica. Now, so we can see what's going on, let's change the scale for the y-axis from -6 to 6 to 0 to 1. Now we see that when petal width is close to 1, the widest, then we will get a high score for Virginica. Triple bam! At long last, we have crinkled surfaces for setosa, versicolor, and Virginica. Now we can plug in the petals and sepal widths from the iris we found and run the numbers through the neural network and predict that this iris is versicolor because that output value, 0.86, is closest to 1. And that's it. So we were going to do more, but we had some technical difficulties and we're close to the top of the hour. So what I think we'll do is we'll stop right here and I can take a couple of questions if there are any questions. So I will exit from presentation mode and take any questions anyone has. Is anybody there? Hello?
Yep. There are no questions as of now on this
Well,
chat.
that's okay. I can always just play ukulele songs.
So
Anyways,
that would be all.
if there's no questions, then I guess that's it for me. Thank you very much. I really appreciate it.
Do we get another song?
Yeah, sure. One more song. Thank you. Thank you so much. I appreciate the opportunity to talk about neural networks to a bunch of people just about to start a crazy hackathon. Good luck with your 36 hours. StatQuest. Bam.
Yay, thank you so much.
Thank you,
I
guys.
express my sincere gratitude to Dr. George Starmer for taking out his time from his busy schedule to enlighten us all on this topic. Thank you so much, sir. And this
Yep.
session is a part of AccessDenied'21. It is a 36-hour mega hackathon conducted by IETE-ISF from 19th of March to 21st of March. It will actually start in another 30 minutes. So there are exciting cash prizes awaiting. The winner gets a cash prize of 20,000 rupees, runner-up 15,000 rupees, and the second runner-up gets 10,000 rupees. There are also track-specific prizes and also other special mention prizes. We'll have similar sessions with other eminent speakers throughout the hackathon for the next 3 days. So stay tuned for that. Also, join us live on YouTube to witness the inaugural ceremony at 8 p.m. tonight. That is in another 30 minutes. I once again thank Josh Starmer for enlightening us on this topic. Thank you so much. Thank you, sir. Thank you, everyone. See you all at the opening ceremony at 8.
Okay. Bye. Thank you.
Thank you, sir. Bye.
Thank you.